Good day, Miss Ann here. Today we are talking with Josh Saunier. Josh is a director at CGI and he works on this really cool project called LEArN. He's going to tell us all about it. Welcome, Josh. How you doing?
Hi, I'm doing great. How are you?
Good, good. So we want to hear all about LEArN, but before we get into that, I want to learn a little bit about what you do at CGI.
I am a director of consulting delivery, and I coordinate technical resources. The way my team works is when other teams need experts, my team has them, and we loan them out temporarily to help the projects get over trouble areas.
Okay, so a technical resource is a person who does technical things?
Yes, they have particular sets of skills. Sometimes they are in programming. Sometimes they're in management tasks. Sometimes they're in communication, math, science, across the entire board. And so whenever a project of some kind needs a particular kind of expertise and my team has it, that person can volunteer to go onto that project for a week, 2 weeks, sometimes a month or more.
All right, well, great. Well, thanks for sharing that with us, Josh. And now we're ready to learn a little bit about the LEArN project. Tell us what this project is.
LEArN is an initiative that helps CGI and teams at CGI cooperate with local governments, nonprofit organizations, and so on, and schools to study what it is exactly that we can do in pursuit of smart city initiatives.
Okay. And is LEArN a national effort? Is it a local effort? Where is it bound geographically?
Yeah, LEArN right now is Lafayette. It's Lafayette
Okay.
Engagement and Research Network. So CGI in Lafayette partners with the University of Louisiana, for example, and Lafayette Consolidated Government to explore what we can do, taking measurements, studying the weather, studying air quality, water quality, and things like that.
So would the information that you learn from LEArN, would it be just for the Lafayette community or could it be used other places?
It could be used anywhere. Let's say we learn some particularly useful lessons about water quality because of an instrument that we designed and built in Lafayette. Once the instrument's built and the lessons have been learned, we can bring that instrument anywhere in the world and use those lessons to improve that area also.
All right. And so smart cities, you use the word smart cities. Tell us about what that is.
So the smart city is a version of the city that's a layer of data on top of the city that we can learn things from. But we don't just learn from those. Once we've learned, we can use that same layer of data to drive things. Instead of just listening to a sensor about traffic levels, I can tell a traffic light based on what I'm learning to change the length of a red light, or to shorten a green light, or to heighten a sensor somewhere else in the city. So the data comes to us, but we can also send data out to those places.
Very cool. And so what is the smart city technology specifically that the LEArN project is using now?
The LEArN initiative right now is using air quality sensors. We have an instrument that we designed that is measuring ozone levels, particulate matter levels, temperature, relative humidity, things like that. And they're all being incorporated into an air quality model. So we could watch, for example, compare temperatures from all over the area. So the LEArN initiative has a website, learnlafayette.com. And if you go there, you can learn a lot of great things about exactly what it is we're doing, what air quality is, what the insides of the instruments look like, how the data is being handled, and you can even request a sensor yourself.
Okay. Now, is that something specific to the Lafayette community, or what if someone's watching this in Michigan?
Right now, the sensors are for Lafayette, but
Okay.
Definitely on the roadmap is to share those elsewhere.
Got it.
If you're in Michigan and you really want one, do not hesitate to contact us. We might be able to put one together and send it.
All right, sounds good.
So as part of the LEArN initiative, we have a dashboard. As these instruments, the air quality sensors, are placed in and around Lafayette, each one of them is communicating to a central location via the Wi-Fi at those places, and we're collecting all the data from those sensors. What you see here, I can zoom in actually, is a map of...
That's what I was just about to ask.
Yep, is a map of Lafayette with all of the deployed sensors right now. For example, UL has sensors at bus stops, at Cypress Lake, for example, and things like that. So what I'm going to do is go to the Cypress Lake sensors. And right now what they're doing is making sure that the sensors are active, that they're stable, and that there's no error in the data that they're taking. So this will take a second to run the background. So we see this temperature. We have the ozone in parts per million. We have two different ozone sensors. We have particulate matter, and we have relative humidity. I said we have two ozone sensors. We actually have three ozone feeds, because one of the feeds is taking in the raw ozone data, doing calculations on it, and representing it having been calibrated. So what I'm going to do now that we know that that sensor is alive and it's giving us information that's up to date. Okay. Our last data point came in at 4:30 this afternoon, so just before we launched the page. I'm going to filter on this side. This is a list of every sensor we have.
Okay, got
it. And we don't necessarily want to see them all at once. So
right.
I'm going to filter this and say Cypress. So
Could
now
we see them all at once?
Oh, sure. I just removed the filter. This is all of the available sensors.
Okay.
At all the different locations. All of the things. When I say sensor, it's one sensor inside an instrument. The instruments are called things. So what I'm going to do is limit this to Cypress so that we can see all of the available sensors in Cypress, and we're going to view temperature. So if we scroll down now, we can see a graph of what the temperature looks like. We see a couple of interesting things. We can choose how much of the data that we want, what's the period we want to look at. So I'm going to go ahead and get another week rolled into there, because it looks like we have some gaps, maybe power outages that stop. Wow. Here we go. So one of the things to notice here, I'll actually zoom in on this area. If we look at here, we have May 1st, May 2nd, May 3rd, May 4th, and so on. One of the things we notice on temperature is that there is some sort of cycle happening. There's a hill and a valley, a hill and a valley, a hill and a valley. So this isn't random data. We know that the sensor's working. We know that it's actually measuring something. In this case, a high temperature corresponds to late in the afternoon, and the lowest temperature corresponds to right before dawn. Those are the things we would expect, because for example, the city or the building that this is on is absorbing heat from the sun all day long. As the sun starts to go down, now that temperature is going to drop. That's very consistent with what we as instruments that measure heat during the day already know. Days are hotter than nights, and as the night goes on, the temperature continues to drop. So if we look at these peaks, these little mountaintops in the data, it's every day about 5 o'clock. So we have a 24-hour cycle on these peaks, which means there's a hottest point every day, and it's about the same time. That is consistent with what we already know to be the case. So that gives us confidence that what the sensors are telling us is meaningful. And there are analyses we can do on this, for example, seasonal analysis and different things where we can pull out or filter out this 24-hour or this 12-hour cycle. And then we also will notice as we go for even more data, let's see how far we can go back, January till now. We'll see how much it's going to give us. What we'll see is that the temperature slowly climbs as we move from winter into spring. It's only going to give us April. But if we go back to here, let's go April there and January here.
And is this just one sensor that I'm looking at?
Yes, this is only the temperature sensor that we chose.
Okay.
Reload data, that's what I was looking for. Okay. But we can certainly, I didn't pick a date. That's what it was. So we'll go to, let's say, March. January to March 1st should give us some cold. there's a limit to how much data we can pull in, so we can't show 6 months all at once,
Okay.
which would have shown us. But this, for example, as we can see where there are cold spots and warm spots, stable times, drops. There's the 12-hour cycle here, or 24-hour cycle in the days, but there's also a rise here. So there's an increase that's happening at the end of February, beginning of March. So we have small trends, which is by the day, and we have larger trends, which is by the week, by the month, by the year, things like that. That's the sort of analysis that we would do in the background with our what's called we have streaming analytics and background analytics that we run. So streaming analytics would take data points in what's called the fast data as it's coming in, and do calculations. Like calibration is a streaming calculation. As we get data, right when we get it, we do a calculation and keep moving. These long-term trends are things that can be pulled out behind the scenes and presented in a different way. So this is what the data streams look like. If we wanted to say, for the same period, let's look at an ozone, SM50 ozone uncalibrated. How about that? Just to show you another thing that's happening. And while we're at it, let's see if we can throw in a relative humidity.
And so this is all the same sensor?
This is the same instrument.
Okay.
One sensor measures temperature and relative humidity. One sensor measures ozone. One sensor measures particulate matter, things like it. The instrument is a collection of sensors.
Okay, so the one box has several sensors in it, and each sensor is measuring a different thing. And as I'm looking at this right now, I'm seeing, is that 2 different sensor measurements?
Yep, this is temperature in blue and ozone in green.
Okay.
And so if we look at this, we can see that one goes up, the other one goes up. This one goes up, that one goes up. But here, something different is happening. This one went down and up, and the green one, the ozone, went down really far and came up again really far. So these are related, but they're not the same measurement. So how they're related is one of the things that we're interested in. How is ozone related to temperature? Is there some relationship we can exploit?
Okay.
And use for other things? Now, let's say I'm going to take out I'm going to hide the ozone measurement and look instead at relative humidity, and you'll be able to see a very interesting relationship that we know to be the case, and again, gives us confidence in the behavior of the sensors. Okay. So we'll allow this to refresh.
Dig deeper for us about when you use the phrase gave us confidence about the reliability of the sensor.
Sure. It's very, very easy. For example, this sensor, when it's taking data, I could just have it take data and it could give me random numbers, or it could say 5 every time I asked. The sensor would be working, but I wouldn't have confidence in that data because it's supposed to measure temperature, and temperature isn't always 5. So when I initially install a sensor, I want to see behaviors I know are true. For example, the days get warmer as they go on. In winter, there's less variation in the day and the night, things like that. So when I say confidence in the sensor, it's that I am moving past whether or not the sensor is turned on, and I'm moving on to, is the sensor giving me good information or not? Okay. So, and those are all things that our team are concerned with. The team needs to be concerned with, can I turn it on? Does it turn on correctly? Are the sensors interfering with one another? Sometimes, for example, if I have 2 kinds of sensors, I might have them reporting each other's data by accident. If I have 2 students, for example, in a classroom, and I say, you watch the left door and you watch the right door, and raise your hand when someone comes in. They may confuse left and right and report each other's data. Okay. But looking at the data, we can see, oh, actually, they switched left and right. We do the same. Sometimes that can also happen with sensors. Ozone is reporting temperature, and temperature is reporting ozone. Really? Because of the way something is reporting. Okay. The sensors are completely different, and the ozone sensor does not know anything about temperature, and the temperature doesn't know anything about ozone, but the way that they're communicating, we can have them reporting in the wrong direction. Things like that can happen. So it sounds like what I'm hearing is the sensor and the things give us really good information, but we as humans still have to be
critically looking at the data.
Absolutely. The sensors are reporting what's called raw data. They're sending numbers. We have to do the calculations and we have to interpret that data so that we know what it is we're measuring. At the end of the day, the sensor is actually just looking at a voltage and reporting a voltage or a current, not a temperature. It's converted, it's converted into what are called engineering values. There's a voltage that's measured. A calculation happens normally in the sensor or inside the instrument that turns that voltage measurement into a temperature calculation. And so that temperature calculation is what gets reported to us. So when we see a value that we don't have confidence in, one of our first questions is the instrument calculating things correctly? So that's where we troubleshoot.
Okay.
If the calculation works, then we say, is the sensor measuring the voltages or the currents or whatever else it's measuring correctly? That's another place we can troubleshoot. If all that's working, then we have to step outside the instrument and say, is the way we're collecting this data working? If it is, we step out even further and say, is the way we're passing the data to the dashboard working correctly? If that is, then our problem is beyond anything that we're doing, and it might be temperature has gone crazy. So,
gotcha.
But we have to be able to troubleshoot at every part of the process, from the way the sensors turn on, all the way to how does our dashboard look on a browser, and everything in between.
Got it. And so if you got, for example, all 5 Celsius, your first assumption would not be, oh, wow, the temperature must now be 5 degrees all the time.
Yes, that is 100% not what we would do.
Okay.
If we have a repeating value like that, especially one that is not intuitive, 5 Celsius, that's cold. It's late spring. It's definitely not cold, and it's definitely not exactly the same amount of cold every time we check. So we would say that's a reporting issue. Let's see what's going on. Sometimes a sensor's communication will go faulty, and the way that we communicate, the sensor stops reporting, but the system that we use to communicate that data is still working. So it says, last thing I heard was 5. So guess what? I'm saying 5 every time because it's the only one I have. And so we would use our troubleshooting procedures to determine, is it the communication that's wrong? Is it the sensor that's wrong? Is it the instrument that's wrong? Is it the dashboard that's wrong? But we would definitely know something's wrong. Sometimes a sensor will report that we'll take measurements and we'll get something that is so wrong, even if you don't know if it's hot outside, you know it's wrong. For example, if I'm looking at temperature and I get a measurement of 4 hot dogs.
4 hot dogs?
Hot dogs. That's wrong anyway. Any way you want to look at it, that's wrong.
Okay.
That means a different sensor is reporting in this communication stream. Because mine does not do that. These sensors don't measure hot dogs. But if that's what we're seeing, those are called the units: degrees Celsius, parts per million, percent relative humidity. Those are the units we look at. So we look at not only the value of a measurement, 5, but we look at the units of the measurement, degrees Celsius. And so either of those can tell us something is wrong. A simple way we can tell something is wrong for temperature, and everyone has done it, is it's hot outside and you see 25. Well, 25 is really cold if you're used to Fahrenheit, but 25 in Celsius is warm. And so mixing up those units, Celsius and Fahrenheit, could make you think your sensor is wrong when it's actually a setting of some kind on the sensor that's wrong. Oh, it's reporting Celsius. That's what it's supposed to do. We were expecting Fahrenheit, so we thought there was a problem, and there's not. That's how the troubleshooting process works.
So the problem is not necessarily going to be with the machine. The problem is with the human.
Right. That's absolutely, that's a user error. We were expecting, for example, if you look at this and you're expecting Fahrenheit and you see 8, that's way below freezing Fahrenheit, but that's well above freezing Celsius. So in Lafayette, if it were 8 Fahrenheit, we would remember.
Right.
And it wasn't 8 in February, which is what the dashboards tell. I'm pointing with my hand as though you can see it. But here, the temperature was 29. See, I did the same thing. User error. I looked at the relative humidity, which was 8%, and I thought that it was 8 Celsius, and it wasn't.
Okay.
So that was a mistake that I made. Here we have 29 Celsius and 8% humidity. So that's another kind of mistake we can make. That one's easily fixed. I looked at the units and I saw, oh, I was 100% wrong. I was looking at the wrong part of the graph.
Now, do you know why the sensors are measuring in Celsius instead of Fahrenheit?
It's a decision that you make whenever you are building out what's called the firmware. There's software that sits in the instrument that runs those calculations. And so what's actually coming out of the sensor is something like 121 milliamps or 0.2 volts or something like that. That has to be converted into a temperature measurement. And so you make the decision to go to Celsius. Celsius is a global standard. Not everywhere uses Fahrenheit, so we would go with Celsius normally.
Okay. Well, what else do you have to show us on the dashboard?
We can, these relative humidity, there's an interesting pattern that we see when we look at temperature versus relative humidity. And let me drag this across and I will illustrate it. Hopefully it'll let me. What we notice here is that when the temperature goes up, relative humidity goes down. And when temperature goes down, relative humidity goes up. But they go up and down by different amounts. They're clearly related.
Okay.
But they're clearly related, but they're not the same calculation. So that's another, this is the sort of information we might look for to say, oh, is it possible that I only measure temperature and I can calculate relative humidity accurately? Because if I can, then I can stop measuring relative humidity because I can calculate it if I need it. We wouldn't really stop measuring it because we always want to be able to check against the measurement. So sometimes we start off with 20 sensors, but then we discover that the relationships between the sensors are very clearly defined, and we can reduce that to say 5 sensors and still get all of the same information by using calculations instead of direct measurements. So what we can also look at, I will hide relative humidity here, and we'll look at particulate matter. And the first thing we're going to notice, particulate matter is a counter. It's counting how many very small pieces of things are floating in the air.
Okay.
And we have a fan on the instrument that pulls air in and pushes it back out. The air is full of tiny bits of things, and those bits of things pass through the sensor and get counted. So in this case, we have our temperature, and I'm going to choose particulate matter, one of our particulate matter streams. And when it comes up, you'll notice one thing before you notice anything else. Probably. It's, as a data person, I look at it and I notice one thing. We're looking at temperature and it's very nice.
Oh, okay.
This has very flat areas, great big spikes, things like that. It's not as clear what's happening with the particulate matter. There's not an easy once per day hilltop.
I want to know what happened on February 26th.
February 26th, that's an excellent question. Those are the exact types of questions that we ask. We say, I'm looking at this data, something happened. Now, what that is, we would have to then look at what's happening not only on our sensors, but what's happening in the city. For example, we worked with a team of students to examine things that were happening on the dashboards. And one of the things that they discovered is that there might be an increase in particulate matter when sugarcane is being burned.
Okay.
That's one potential solution for what this spike might be. It may just be, we can also see what time of day it was, which was 9 p.m. So at 9 p.m., on 9:30 p.m., February 25th, there was a great big spike in particulate matter, 2.5 micron particulate matter. What that is, not sure. Because it is one sensor, it may be that one sensor, someone was smoking near it.
Okay.
If we look at all the other sensors on campus and they all have a spike, that means it's something else. If we look at all the sensors in Lafayette and they all have a spike around that same time, that indicates it might be a real thing that happened that affects the city of Lafayette and not just the sensor box at Cypress Lake. Now, another thing that's interesting about this is these sensors take readings very often. And so if we have something that happened south of Lafayette that spreads through Lafayette, what we would be able to see on the particulate matter is that the sensors in the south of Lafayette would trigger at 9:30. In the middle of Lafayette, they might trigger at 11. North Lafayette, they might trigger at 12:30 or 1. And so we can watch a front, for example, of particulate matter moving through Lafayette. Or one of the problems we're interested in now is with so many people working remotely and the city going into enforced distancing and quarantine, is did particulate matter drop?
Right.
Because there are so many fewer cars, and we don't know the answer to that yet, but that is a kind of question that we can look at, because we can then compare that to traffic cameras and things like that and find neighborhoods where there was a huge drop in particulate matter or a spike in particulate matter. So we can discover patterns in the way a city behaves, not just one location. We watch how one location behaves, and we look at all the locations together, and we try to find patterns there. And once we find them, we can say, this is how the city behaves. The city gets warmer in the daytime, and it gets cooler at night. Sensors that are on brick buildings or on asphalt stay warmer longer in the evening, things like that. And so we can identify areas of the city that might be of interest for other studies.
So if I'm hearing you correctly, if we're looking at this one sensor, we can get some ideas about what's going on in a bigger way, but we probably can't draw any conclusions based on it.
Not about the entire city. If I have a group of people, let's say I have an entire classroom full of people, and I pick one person and say, what's your favorite color? And they say green. I could say this class's favorite color is green, but that would probably not be true. It might be, but it probably wouldn't be. What I would want to do is I would want to ask all the kids, all the students, if I could, and then say, most of the class likes blue, a lot of them like green, so our favorite color is probably a mix between blue and green, or let's try blue sometimes, let's try green sometimes. If I have 100 million students, I can't ask that. What I can do is I take an even sample of the students and I randomly pick, say, 10, 100, 1,000, and ask that same question. That's what we do with the sensors. We can't put a temperature sensor at every location in Lafayette. But what we can do is pick key areas and put temperature sensors there and build a picture of what's happening temperature-wise in Lafayette. What is Lafayette's temperature? And we can start to ask questions about temperature in Lafayette because we have a wide enough assortment of locations doing that. But you're right. One sensor is not going to tell us really anything about what Lafayette's doing. It'll tell us what's happening at that exact location when that sensor took the reading. But you have a network of sensors, and they all are cooperating to give you information about a much larger area.
And so you were talking about cars earlier. Would the particulate matter graph be the one where we find out about exhaust from cars, for example?
Yeah, and we could look at ozone for that. We could look at particulate matter, any of those things. If we were going to build an instrument specifically to track exhaust, what we would do is combine particulate matter, the chemicals that we would expect to see in exhaust, and temperature, and combine those to make an exhaust sensor or an exhaust instrument. But yeah, particulate matter is absolutely something we would check. It's just counting things of a certain size. That's what the particulate matter sensors that we have do. There's a laser, and bits of things float in front of it and interrupt it. And when it gets interrupted, it counts. And so it counts all of the things floating in front of it.
Wow, okay. So it counts the number of times it gets interrupted, and that's what we see pieced together on the graph here.
Yes. And count it 1, 2, 3, 4, and it what's called an accumulator. It accumulates counts in a certain time period and then reports them. The same way you've seen at say a baseball game or a football game, someone stands at the door and clicks as people walk through. That's an accumulator. So you have a sports fan sensor positioned at the gate of an arena, and it counts and counts and counts for 1 hour, and then it passes. Then another sensor comes in and begins to count. So that's a 1 hour time period with a sports fan sensor. That's an accumulator. And the number that's on the sensor at the end of the hour, 680 or whatever it is the number of sports fans that have passed that particular gate. And that's exactly what the particulate matter sensors do.
That's a great analogy. Thank you, Josh. And so a question I have for you, we're looking at one sensor here. Could we look at more than one sensor at one time?
Absolutely. We are at Cypress Lake. Why don't we look at the Student Union bus stop also? There we go. And so I can put the temperature, for example, at the Student Union bus stop, and we can compare it to the temperature at Cypress Lake.
And so while that's loading, for those people who don't live in Lafayette who are watching this, what is Cypress Lake?
Cypress Lake is it's a very small lake. It's more of a pond, but it is a cypress habitat that is on the campus of the University of Louisiana at Lafayette. It's adjacent to Student Union, and it has live alligators and a lot of cypress and a lot of duckwort and things like that. And so it's an excellent place to walk. They have a lot of decks. It's an area that's usually much cooler than surrounding areas because it is a body of water that's in a lot of shade. So that's what Cypress Lake is. I've been there. There are in fact live alligators there.
And you said, do you walk in Cypress Lake?
I didn't know you walk around Cypress Lake. Now there are students whose job it is to clear the water of different weeds. And so they actually have a small boat and very tall boots, and they stand in Cypress Lake and they clear the plants away to make sure that the turtles, the alligators, and the fish can have enough food to stay in the lake.
So only trained professionals do that though, right?
Trained professionals or very daring amateurs. So we have, these are overlaying one another almost. It looks like either they're overlaying.
Have it right, because I can't tell if they're both there.
What we're going to do is this may be a period when the bus stop wasn't actually reporting. We may have happened to choose a window where the bus stop wasn't reporting, so it's not showing up.
So this is what you were saying earlier about just because you said pull these two stops, we can't automatically assume we're seeing both. We have to use our brains and,
yes.
And evaluate the data that we're seeing.
Yes. And so if we go to this most recent window and we don't see the temperature, what I'm going to do is clear the Cypress ozone or particulate matter sensor, because that may be doing it also. Nope, Student Union bus stop. Here we go. So Cypress Lake. So Cypress Lake is reporting, and it looks like the Student Union bus stop stopped reporting. So we can hide that one. And we'll go to the Rex Street bus stop, which is a different bus stop. Rex Street is a street that goes through campus. It starts at the physics building, drives past chemistry, civil engineering, and goes to English, history, and languages. So Rex Street is relatively short, but it passes a lot of great highlights on campus.
Okay. And I'm looking at the Rex Street. If you scroll up, it looks like its ozone was recording today, but the temperature hasn't recorded in a while.
Yeah, excellent point. The last updated temperature sense was 9/12/19, so that's quite some time ago. So that would indicate that some of the sensors are reporting and some aren't. You know what? We can troubleshoot this on the fly. I think I know what this is. One of the ozone sensors is still reporting live. What that's telling me is this is the calibrated ozone, and it is taking the last value that it got and continuing to report it. So 9/12/19, late last year, the last sensing came through for ozone. The calculations, however, run in real time. So it's continuing to report that last one. So if we take the calibrated ozone, let's find the calibrated ozone. This is, oh, nope, it's uncalibrated. So one of the ozone sensors is still working here. So this would indicate that we need to investigate this instrument. because it hasn't reported in a while. So, and if these reported that far back, then they might not show. So what I'm going to do is take the particulate matter off of the, actually what we can do, I'm going to reset so that we don't have to, it's quicker than having to back out through all the data streams. So we'll go to Cypress Lake and we will load the temperature, and then we'll pick another temperature somewhere else and compare them. And we can edit this. That would have been great. We should have done that beforehand to find two sensors and be sure that they were both up to date.
Oh.
But we know that Cypress Lake is live, and so then we can do union. So Cypress Lake temperature is down there. And what we can do is go back 125.20. Okay, so that's January. So we can take the air temperature from the bus stop in the Union and go back to January and compare those from January.
Okay.
So what's going to happen here is it's going to look like nothing happened when it's done thinking. There we go. And so what I'm going to do is choose my end date here. This is UL's main campus. And I'm not sure why. Let's go back even further and see why this is not. Let's go December 1st to.
Do you know how long those sensors have been there?
They've been there well over a year.
Okay. What are the lifespan of the sensors?
The sensors themselves can go a very long time, but what happens to sensors is once they've been calibrated, they do something called drift. Here we go. They do something called drift, where we have a value we know to be true. We compare what the sensor's saying, and we calculate that relationship so we can make a correction. Over time, that correction begins to drift away. And so when we calibrate an instrument, it tells us the temperature as close as possible to the real value. A year later, it might always be 5 degrees off. 2 years later, it might be 10 degrees off. So over time, the sensor becomes very inaccurate. But you can recalibrate and bring them back because the drift happens hopefully in a very consistent way. Now, if we look at this comparison from December of last year, 2 weeks in December, the Student Union bus stop and Cypress Lake temperature sensors have a relationship that we find very, very encouraging. Not only do we see our peaks every day, which we like in temperature, but we can see that they are agreeing on these peaks. And they're agreeing on longer term behavior. So in December 18th, the temperature was very low. It gradually crept upward all the way to 30th of December when another cold snap hit. And we can compare this to actual weather reports from the time and show that the sensors are telling us what they're supposed to be telling us. But in this case, we would expect these temperatures to be very close to one another because these two sensors are very close to one another. One is on Cypress Lake, which is here, and one is at the Union bus stop, which is here, which is about 50 yards. So we would expect these to be very, very close, and they are.
So is the one at the bus stop warmer?
The one at the bus stop, let's see, is actually they pass each other sometimes. So they're within the range where we would expect them. I mean, they're close enough that they cross. Sometimes one maybe is in the wind a little more. One of them. Now we do see here an interesting thing that we can try to figure out. When there is a large peak, the main campus, the Cypress Lake sensor, continues to report, but the bus stop stops reporting.
Really?
There are 1, 2, 3, 4 times that this happened. And so what we might ask is what else is going on with that bus stop sensor at those times? And so we would then compare particulate matter, ozone, relative humidity, things like that. It might have been raining and there might be a leak in the box. So when relative humidity gets high enough, we can, in fact, why don't we check that? the bus stop relative humidity. We'll check it. So an extremely high relative humidity measurement may indicate that you have a leak. It could indicate that the box has been submerged. It can indicate a lot of things. And so what happens with any kind of sensor, there's what's called effective range. Whenever you try to measure, for example, a thermometer in your kitchen, you might have a digital thermometer that you use to measure meat or cake temperatures. And it works well on the temperatures in your kitchen. But if you tried to use that kitchen thermometer to measure, say, the inside of someone welding or the surface of the sun, it wouldn't work because it's outside the effective range. That sensor was not designed to tell you that. I, for example, am a very good way to measure roughly things between 1 meter to 2 meters tall, because I'm a person and that's the range of most people. A person is not a great way to measure something that's 1 mile tall. That's too tall.
People is that? Yeah.
Yeah, that's too tall. And people are also not a great way to measure things like a micron. That's just too small. So that's way outside the effective range of a person to be able to either use their hands or their arms to measure things. But a car, how wide is a car? I don't know, 2 of me with my arms out, 1 of me with my arms out. That's an effective measurement range. How big is a basketball? About that big. So that's in my effective range. How big is a school? I can't show you that with my hands. So it's outside the effective range. So if we look at relative humidity here, it looks like nothing special is happening. So relative humidity might not be the answer. It might be particulate matter. It might be ozone. It might be any of a number of things. But we have to look, when we see an odd behavior in a single sensor, we have to look outside that sensor into either other sensors or what's happening in the area of that sensor. It could have been a power failure. It could have been a networking issue. It could have been any number of things. But those are the kind of things that the data tells us. There's an interesting thing happening in the data. We thought one thing was going to happen and a different one happened. Okay, well, let's dig in a little bit and see what it tells us. We can ask the sensor, we can ask the data, we can ask the box that the sensor's in. All those things might give us good information. And as we continue to collect all the information from all these sensors, we begin to understand what Rex Street, what Cypress Lake, what the campus at the University of Louisiana at Lafayette, and what the city of Lafayette are all doing in terms of temperature, ozone, and other things. And all those things get put together and we can build out an air quality profile of campus, Cypress Lake, or Lafayette. And over time, we can show if measures that we're taking to improve air quality, for example, are working or whether they're not working.
Wow. Well, Josh, this has all been very interesting. I've learned a whole lot, so thank you so much. And before we go, what I would love to hear from you is if you have just one takeaway, maybe 1-2 sentences while you're showing us this graph right here. Would I call this a graph? Is that?
Yes, absolutely.
Okay. While you're showing us this graph, if you could tell us one takeaway you want us to leave with.
One takeaway about everything we've talked about today is that you don't have to understand everything about a city to get useful information from it. Sensors are not smart. Sensors are very dumb, but they measure something very carefully, very, very often. We collect all of that information, and we as people can then use computers to build out models of the city and get a version of the city that's built out of our models. We can then study those models instead of studying the city itself and make predictions about the behavior of the city or about things we can do to make life in that city better.
Great. Well, thank you so much for your time. And I can't wait to tell other people about this. As you mentioned before, there is a way to get more information off the website, even learn about the potential of receiving a sensor. And Josh, any closing words before we go?
I really appreciate the opportunity to talk about LEArN and to highlight the really great work that our teams have been doing. And any questions anyone has, feel free to contact me through the LEArN website, and we'll get back to you. And I appreciate the time.
All right. Thank you.